So, yeah, why don't you tell me what you remember or what you've learned so far about parabolas?
Okay. So basically, um, they're similar to like linear with
Yep.
like needing points,
Mm-hmm.
but they're different because they have a turning point.
Mm,
That's what makes them curve.
nice. So you're saying shape-wise, we were used to originally seeing a line like this that was linear. Now we have something else that looks kind of like a U shape. And you mentioned that it has something that we call a turning point.
Yeah.
Okay. Yep, that's good. Um, can you tell me anything more about it? Why is it that it might have this shape? Remember, we spoke a lot about how the equation of the line is like this, y equals mx plus b, and then that produces a straight line. Where does this shape come from? Or well, yeah, what other things can you tell me about parabolas?
Well, the equation is like different. The
Yep.
equation's y equals x squared.
Mm. So this is a specific parabola. It's the parabola that looks like that.
Yeah.
Um, so this is like a specific line. Could you tell me, or do you remember what the general form of a parabola might be? Or the general
Not
equation?
sure.
That's okay. If I write it down, let me know if it rings a bell. So sometimes they write y equals ax squared plus bx plus c. Does that look
Oh
familiar?
yeah.
Hmm. So this is the equivalent of our like y equals mx plus c or mx plus b. This is the general form. Um, so here, a, b, and c are like the equivalent of, how we had m and b in the previous one for lines. Um,
Yeah.
these are constants. So if you want a parabola, these will actually be numbers. Like it might be the number one, two, and three. And depending on these numbers, we will have a different parabola. We might have a parabola here, a parabola there, and so on.
Yeah.
Um, now, the main goal of a parabola, or with this topic, is to be able to go from equation to graph. So that's what we spent a lot of time doing when we had the line, right? We had the line y equals mx plus b, and we spent a lot of time looking at what does m, what does b mean, and how we can go from the equation to the line, or from the line back to the equation. So we have the same goal when it comes to a parabola. Um, now, maybe based on what you've learned, or based on like maybe how we approached it with a line, how do you think we can do this process? How might we be able to go from a um, how might we be able to go from an equation like something like x squared plus 2 minus 2x plus 1, something random like this? How would we be able to go from this to an actual drawing on a graph? What are your thoughts?
You could make a table of values with each of the different points to mark.
Very nice. So that's always an approach. That's how an equation actually goes to a graph. You're exactly right. We could sub in different x values, and we could find out what the y values is, and we could get a pretty good understanding of the parabola. That's really good. Um, now, so you can always have that as like an option number one. But just like a line, we can also do that. Remember when we were doing lines, there's easier ways to find the equation of the line. If you know the y-intercept, like if you know b is the y-intercept and m is the gradient, you can sort of instantly graph it, right? Even if you don't test points.
Yeah.
So in the similar way, that's the ideal thing. If we can look at our equation and sort of know what the graph is. Um, and for that purpose, there's one key technique or key skill that you learn when doing parabolas, which is factorizing. Have you learned this yet?
Yeah.
Hmm. How would you describe what the technique or process of factorizing is?
It's what you do to make a quadratic.
Yep.
Is it?
So to
Yeah.
sorry, were you going to add something?
No.
Mm. To clarify, this is already a quadratic. So uh, what we have here is a quadratic equation already. Um, Quadratic simply means anything with a squared term. So as soon as you have an equation where the highest power, like where you have this x squared term, it's already a quadratic. It's like the difference between when you had y equals to just like uh, bx plus c. This is called a linear term, right? As soon as you add this ax squared term, it now becomes a quadratic.
Okay.
So quadratic is already this, but you're right. Factorizing involves doing something to a quadratic. Can you remember what it might involve? Or you can give me an example, maybe. What do you remember about factorizing?
Well, the goal is to make the it's to like simplify the quadratic.
Very nice.
Yeah.
Let me ask a follow-up question. So you mentioned the word simplify, which is really good. What does it look like to simplify this? So you're saying we're changing this equation into something else. What does that quote unquote simplified version look like?
I think x squared plus bx plus c. But oh wait, actually, I'm not really sure.
That's okay. Good guess. This is not quite right. This is a just a simpler version of a quadratic where a equals to one. Sometimes they call this monic, which we can get into after. Not super important at the moment. Um, but the simplified version, it's probably more correct. It's absolutely, definitely simplified. Sometimes this is called the factorized version.
Oh, is it x plus a, x plus b?
Awesome, very, very nice. We
Okay.
want to turn this into something like x plus. We can use that. Oh, actually, just because we use A, B, and C here, let's come up with different letters. Maybe D and E, something like this. Um, or yeah, for now, I'll call it x minus D, x minus E. Very good. We want to turn this equation into this. Now, I'll ask a couple questions. First, uh, why do you think this is simple, or why do you think this is nice? Remember, our ultimate goal is to sort of graph this parabola. If we get it in this form, why is that pretty nice?
It helps you find the two x values.
Really good. It helps us find the two x-intercepts. Um, Now, why is that the case? If I go from having to graph this to instead having to graph y equals x minus d and x minus e, why do I know the x-intercepts pretty easily?
Because you know that both x minus d and x minus e equal to zero. So that means e and d are the values.
Awesome, spot on. X-intercept means y equals zero, right? If we're looking for our x-intercepts, we're looking for when our graph touches this line, which is where y equals to zero. And so if I'm looking for x-intercepts, I set y equal to zero, and we're solving for this, x minus d, x minus e equals to zero. And if you have two things that multiply to equal zero, the equation is true if one or both of these things are equal to zero. So when is this true? It's true when x minus d equals zero, which is the same as saying x equals d, or when x equals to e. And so those are your intercepts. Your parabola, oops, will have the intercepts of d and e. Um, cool. So hopefully we can see the motivation of why factorizing is important because it helps us get to this stage. And as soon as we get to this stage, it's quite easy to graph. Um, does that make sense? Any questions about this so far?
No, it makes sense.
Cool. So now the thing we got to learn is we want to get really good at factorizing. Um, so to factorize, first uh, we will look at factorizing monics, and that goes to the one of the things you mentioned, factorizing monic quadratics. So what I mean by that, actually, have you heard this before? If I say monic quadratic, what do you think this might mean?
It's a quadratic that doesn't have a number in front of the x squared.
Very good. Or another way to say it is it's a quadratic where this a equals to 1. Um, yes, exactly right. So it's like when a equals to 1. So we just have x squared plus bx plus c. Um, so if I give a quadratic, I want you to talk me through how you might factorize it. A monic quadratic, that is. So x squared plus, let's pretend I gave 8x plus 12. If I give you this, how comfortable are you factorizing it? And if you're comfortable, do you want to talk me through how you would do it?
So I'll find two numbers that when they times together they equal 12, and when they add they equal 8.
Okay, very nice. So we're looking for two numbers that multiply to give this and add to give this. What
Yeah,
are those numbers?
6 and 2.
Nice. So you've spotted that 6 and 2 satisfy that. And what would you do with that?
I'll turn them into x plus 2x and bracket x plus 2 bracket x plus 6.
Like this?
Yeah.
Awesome. Very good. So you've got that completely down pat. Let me just really quickly explain, because this seems like a bit of magic. We look for two numbers that multiply to give this and add to give this, and magically we're just saying this is true. Actually, before maybe I give the explanation, how would we confirm hypothetically that we actually have gotten the correct answer? How would I know? Let's say I'm doubting that this is true. How would you convince me that actually this is the factorized version of this?
You could multiply them together.
Awesome. As in, we could expand this out.
Yeah.
Very good. So let's just convince ourselves. Well, let me convince myself. So we would have x squared, then we would have 6x, then we'd have 2x, and then 2 times 12. 2 times 12, or 2 times 6, sorry, which is 12. So notice that thing we were looking for, two numbers that add up to 8, two numbers that times to 12, it exactly works out when you expand this. What I mean is, we have the 6 and the 2, and when we expand, it combines to give 8x. And we have the 2 times 6, and that combines to give 12. And this isn't like a coincidence. So to quickly give you like the explanation, it's our task is to go from something that looks like x squared plus bx plus c, and we want to end up with something that looks like x plus, we'll use the same letters we did before, x plus d, x plus e, right?
Yeah.
If I expand this, so we get x squared, so it's basically the same as this, except with the letters, x squared plus ex plus dx plus de. And if I combine these, you get x squared plus e plus d times x, and then d times e. Oh, maybe I'll remove the times because it looks... So basically, this was our quadratic we started with, right? And
Yeah.
this is what we have here. So if we want these two things to be equal, that's what our aim is. We're trying to find the d and the e that make this equal to this. So we want this expanded version to also be equal to that. For that to be true, well, then we already have x squared being x squared. If we want this to equal this, we need B to equal E plus D. And you need C to equal D times E. And that's exactly where we get that condition from. We're looking for two numbers that do what? Two numbers that add to give the B number here, and two numbers that multiply to give C. And that's sort of where that condition comes from. Because when you find two numbers that add to give the middle and two numbers that multiply to give the outside, you will always be able to factorize it like this. Does that make sense?
Yeah.
Sweet. Okay, so that is factorizing monic. Um, Now, factorizing non-monic is trickier. So this is when basically a does not equal to 1. And technically it's not 0 as well, but yeah. Um, so let me give you an example. Oh, maybe that's... 1 second. Something like this. How comfortable are you factorizing something like this?
Um, I think I know how to do it.
Yeah. Do you want to give it a go first, or do you want to talk me through it?
Yeah, I'll talk you through it.
Yeah, let's hear it.
So you would factorize the two out. So you do two bracket and then just the original equation,
So what would come here?
7x plus 3.
Ah,
Oh,
well,
actually, it'll be 7 over 2x
nice,
plus 3 over 2x. I mean 3 over 2. Yeah.
nice. Yeah, yeah, good stuff.
And then you would factorize the equation inside the brackets.
Okay, and how would you do that? I only ask because now it's a bit more annoying. Technically, it's the same process. We're still looking for numbers that add and multiply. However, here we have like fractions now, so it's trickier to come up with it. But maybe you can have a go and let me know if it's a bit like let me know if you think it doesn't work.
Okay. Actually, I'm not sure.
Yeah, it's okay. It's tricky because usually we don't. By the way, great instinct though. This is a really good skill in math. Whenever you're given a harder problem, try do some steps to then simplify it back to the base case that you know. So that's a really good instinct to have to factorize the two, take the two out, and then say, oh, now we have a monic. Let's try apply the method here. The tricky thing is when we're given these. So this method will work if we had something easier. If, for example, I had the thing 2x squared plus 16x plus 24. If you factorize out the two, you get x squared plus 8x plus 12. And now you have something exactly like we did before. And then you can factorize the monic and everything is pretty good. But it doesn't work when you have something like this and your numbers become now it's very difficult to find two numbers that multiply to give 1.5 and add to give 3.5. Possible, but it's difficult. Um,
Oh, so do you have to complete the square?
Good idea. Completing the square is something uh it's a different technique. There's a way, so what do I want to say to that? So you could use completing the square with this, but there is an easier way to factorize. Like completing your square should be your last resort, unless the question explicitly asks. Does that make sense?
Oh, okay. So
So
would you use the quadratic formula?
good question as well. So completing the square and quadratic formula are kind of one or the same. If they're asking you to factorize, you would use either or. But
Okay.
there is a step you can do before both of those options, which is better, which is easier to do. Um, but good instincts. Both of those are so those will work all the time. Like quadratic formula will work all the time. You can always just plug in your A, B, and C and instantly find out what your this E and D should sort of be. Um, you can think about that as a way to solve it if it's too tricky to find the roots. Just like what we had. So it's a good instinct to have. If you have numbers that are too tricky to factorize, you can use quadratic formula all the time. But before that, there's one other way. So I'm not sure if I'll talk you through it, and then um, you tell me, interrupt me if you remember learning this technique. If you have a monic, so the trick you can do is you imagine you multiply this A term by the three term, but sorry, by the last term you have. So in this case, it would be six, right?
Yeah.
And then you apply the same logic we did before. But this time you do it with this term. So you look for two numbers that multiply to give six and two numbers to add to give seven. So what would those numbers be?
It would be 6 and 1.
Very nice. Yep. Now, once you've found those, what you do is because they add to give this, you basically reverse sort of what we did here. So here our 8x was produced by 6 and 2, right? And
Yeah.
you split it up like this. We're going to do that same thing. So we're going to rewrite our equation, but we write it as x plus 6x. So we rewrite 7x as like 1x plus 6. And that 1 and 6 comes from those numbers that you just came up with. That 1 and 6 times to give this, and they add to give 7. Does this step make sense?
Yeah, I remember this now.
Nice. Could you talk me through maybe what we do from here?
Then you'd sub out the 2x.
Very nice. So we would factorize out x from here because 2x, this term doesn't have a 2. So we would factorize out x, and
Oh
this
yeah.
would turn into 2x plus 1.
Yeah.
And then out of here, what would we factorize?
The 3.
The 3, very nice. And again, we get 2x plus 1. And then from here,
It would equal bracket x plus 3, bracket 2x plus 1.
good. We can sort of factorize out this 2x plus 1. And we would get this. Whoops. Okay, very nice. So this is your go-to first if you can't if you have a non-monic. But sometimes the numbers are messy and you can't come up with it yourself. You can't come up with the numbers that add and multiply to give what you want. And that's when these other techniques come in play. So let's talk about them now. Let me think about how I will motivate this. Um, okay, maybe we will take a little detour. We have been saying that all this time, our main goal is to convert a parabola to a and factorize it, right? To convert our quadratic into this factorized form. A
Yeah.
natural question that needs to be asked is this always possible? I.e., is it always possible to actually convert it into this factorized form? It's all good if you don't know, but what would your guess to that answer be? Is it always
Probably not.
okay? Why do you think that? Is it just because it seems like a pretty big thing to say it's always possible, or is there any or is there any example of or further reason other than intuition as to why you think it's not possible?
Um, Wait, so what's like the question again?
Yeah, for sure. My question is, if I give you a parabola, any quadratic equation, like something random, like 3x squared plus 2x minus plus 100, is it always possible for this to equal some factorized form, like x plus something, x minus something? Is this always possible?
Actually, yeah,
It looks like it's possible.
yeah.
Like maybe you're thinking, surely we can use one of these approaches and then it'll, or quadratic formula, and we'll always be able to get it in this form. Um, so I won't give the answer yet. Once we're in this form, how did we say we can graph our parabola?
By finding the x values.
Yep, we would find these two numbers and it's pretty simple. We just get a parabola like this, right?
Yeah,
So anytime we factorize our parabola or our quadratic, we will have a parabola with two x-intercepts.
yeah.
Now, my follow-up question is, do all parabolas have two x-intercepts?
Oh, actually, no.
No. Nice. And does that change your answer to this?
Yeah,
Yeah. Because parabolas can also look like this and have zero x-intercepts, or they can actually look like this and have just exactly one x-intercept. Now, if you have a parabola like this, it's impossible to factorize it, right?
yeah.
It's actually not even possible to factorize it. Um, and this is where we motivate this technique of completing the square. This is where that technique comes from. Because remember, what was our ultimate goal from the very start? My ultimate goal is I want to go from an equation to a graph. And sometimes we can factorize it, and that's really good. If you factorize it, you can instantly get your graph. But other times, your parabola doesn't even have a factorized form, in which case it's not possible to factorize, and we won't even be able to um, find the graph. And so that's where this second technique comes from. It can be used for more than this case, but I'm just motivating it. That's where it initially comes from. We use completing the square so that we can actually graph things that look like this. So let's talk about this. So the answer to this, no. Um, Now this is a tricky technique to remember, or at least when I first learned it, I remember it was like there's so many steps and it's easy to forget. So it's an easy technique to mess up, but let's talk about it. So again, I'll give you an example, and I want you to talk me through what you remember. If you were told to do completing the square on something like, uh, 1 second. Hmm. How would you do completing the square on this?
Um, I'm not actually sure. I've
Oh,
like
no worries.
forgotten.
No worries at all. It's a very easy thing to forget. Now, it doesn't matter if you've forgotten the process. Do you remember what the end format looks like, or what the aim is?
It's to get x plus a, x plus b, isn't it?
Not so sometimes you can do completing the square and get to this. You're right. But like we talked about here, sometimes that's not possible. If we have a parabola like this, that's not possible.
Yeah,
So this is going to be one of those cases. And so actually, our end format is not going to look like x plus a plus x plus b. It's going to look like this: x minus h or x plus h squared plus k. Have you seen this before, maybe?
I don't think so.
That's okay. So this is a different format. Just like we had like the general form, that's sometimes called this. We had the factorized form, that's sometimes called this. This is what the name of this is sometimes called turning point form, and I'll explain why. Um, and so our goal is going to be to end up in this. Um, and I'll explain why that's actually a nice place to end up. Now, the main thing about completing the square is you want to turn this into a perfect square. So, for example, if I had instead written x squared plus 4x plus 16, how would you factorize this using the normal method we know?
I would find two numbers which multiply to 16 and add to 4.
Oh, sorry, I've done this wrong. I meant to write this. Yep, sorry. You're exactly right. Now, what are those two numbers in this case?
2 and 2.
2 and 2. So what will be my factorized form?
X plus 2, x plus 2.
It'll be x plus 2 times x plus 2 or x plus 2 squared, right?
Yeah,
And that's super clean. Now, the way you do completing the square is basically you force, you try and change the number, this constant number that you have at the end, so that you can factorize it in this form. And then it looks like this. What I mean is, we didn't have x squared plus 4x plus 4. We had x squared plus 4x plus, I think it was 20 I had written, right?
yeah,
Now, 20 isn't going to give us this same thing. However, instead of writing 20, if I wrote plus 4 plus 16, do you agree this is the same as just writing 20?
yeah,
Now, I know that this, what I have here is the perfect square, right? This
yeah,
will turn into x plus 2 squared, and then I just have this 16 on the outside.
yeah.
Um, Now, why is this good? The reason this is good is because actually this can be graphed very easily. So to explain, and that's why this turning point form is sort of a helpful thing. Our original parabola looks like this, right?
Yeah.
Do you have any guesses as to what this might look like?
Like, what do you mean by that?
Yeah, my question is, how might you graph this equation? Are you able to know what this parabola would look like on the graph based on this form?
I'm not sure.
That's okay. So let me give a hint. This is the parabola x squared, right? Where would the parabola x minus h squared look like?
It would be more to the left, wouldn't it?
Close. It would be to the right because
Oh, okay.
you tell me why though. If I have this graph, y equals x minus h squared, where's my x-intercept?
It's I'm not sure.
That's okay. So remember this technique. This technique. So if y equals to 0, this is like saying x minus h, x minus h. So my x-intercept is what? It's x equals to h.
Yeah,
Does that make sense? Like if this was x minus 1 squared, my x-intercept is x equals to 1.
yeah,
So the parabola, oops, would be wherever h is, it'll be to the right like this, right?
Yeah.
Now, instead, what if I had y equals x squared plus 3? Oh, sorry, plus k. Where would that be?
It would move up.
Very nice. We would take our original parabola. Um, so let me put it like this: y equals x squared. So y equals x squared is the blue one. Y equals x squared minus h is the red one. Y equals y equals to x squared plus k is the black one, right?
Yeah.
And so um, what we see is when we have x minus h, this shifts our parabola left and right, depending on if it's plus h or minus h. If you have plus k at the end, this shifts your parabola up and down.
Yeah.
Can you see that? And that's why this form is actually really nice to have. You can't graph your parabola directly if you have this, but if you have this, we know my parabola is going to be shifted 2 to the left and 16 up.
Oh,
Or
okay.
the turning point is going to be 2 to the left and 16 up. So I know instantly this parabola is going to be 2 to the left and 16 up. It's going to start here, and then I'm just going to draw it like that. Whoops. Does that make sense?
Yeah.
Yep. So that's the advantage of turning point form. And that's the initial reason why we want to do completing the square. Um, before I move on, are there any questions about that?
Um, I'm just like curious, like
Mm,
if you're graphing it, don't you need like the entire table to like mark it accurately? Like
mm.
the
Great
entire
question.
curve?
Great question. You're right. If I wanted to do a perfect graph, I would need. You're saying like surely you need more points. Is that what you're saying?
Yeah.
Yeah. How many points would you need?
I think like 8.
8?
Yeah.
Sorry. Yeah. But wouldn't you say it's still not perfect? If I want a perfect graph, don't I need more than 8? Like I want to do the points in between.
Yeah.
So the reason I'm purposely being a bit um annoying is there is no such thing as a perfect graph in that sense because unlike a line, with a line we had all like even with a line, I guess, it was clear where every point was because it's a straight line. With a parabola, unless you're showing every single point, you're always filling in the gaps somewhere, right?
Yeah.
Like, yeah, just doing 8 points, someone can still say, "Oh, what about in between?" You don't know exactly where it is. Um, so that's why there's no such thing as a perfect graph, first of all, because you can't test every single point. But maybe the real question you're saying is like in an exam sort of thing, surely we need to test more points. Um, and the answer to that is it sort of depends what your teacher wants. The general rule of thumb, though, with a parabola is you don't need to actually have every point. The things you definitely need are turning point, x-intercept, and y-intercept.
Okay.
So if you include these 3 points in your graph, then you're pretty sweet. You don't have to worry, unless they've told you otherwise. So in this case, I am missing my y-intercept. How would I get that?
Like for the graph above,
For this one, yeah.
but there's no y-intercept.
Yep. There's no y-intercept I've drawn because I've drawn it like this, which is a bit lazy for me. If I draw the full thing, this parabola keeps extending, right?
Yeah.
Sorry, that is a horror parabola. Let me. Yeah, that's not much better, but we'll go with that. Um, it eventually does touch the y-axis. Um, so how would we find that y-intercept?
Um, by writing it as an equation.
Yep. So we already have this equation here for it. Um,
So
how
you'd
would
make
I?
x 0.
Nice. So I would chuck x equals 0. I could do it either in here or here. It doesn't matter. So if I do x equals 0 here, I mean, because previously we had x squared plus 4x plus 20, right?
Yeah.
So we instantly get, if x equals 0, these go away and we get 20. So our y-intercept is 20. So this, all things, like if it's a normal teacher, they're happy with this. Um,
Okay.
yeah. Any follow-up questions on that?
No. Well,
Okay.
this is like this
Mm-hmm.
one formula we used like in class.
Mm,
I just want you to like explain it.
of
It's
course.
minus b over 2a.
Where does this come from?
Um,
Or what does it represent? Is that
oh,
your...
you needed to find the axis of symmetry.
Yeah. So the question is, sometimes you're asked to find axis of symmetry and this formula comes up.
Yeah.
Mm, okay, great question. Um, Let me think about how I'll um in link this to what we've been doing. So, um, okay, so first I'll explain what this is. In terms of why it's true, it's a bit tricky to explain without a little bit more knowledge of math and like this parabola and calculus stuff, but I can explain what it represents. So why don't you tell me first? So you mentioned this formula is sort of linked with axis of symmetry.
Yeah.
Um, so talk me through that. What do you think this represents?
Like the axis of symmetry.
Okay, in that case, like what does axis of symmetry mean?
It's the line that goes down the parabola, isn't it?
Nice. The middle of the parabola. Is that what you mean?
Yeah.
Yep, very nice. So the axis of symmetry is like, yeah, if it's like the middle of the parabola. So another way of thinking about the axis of symmetry is it's the x value of the turning point. Does that
Okay.
make sense? Wherever the turning point of the parabola is, that x value, that's what the axis of symmetry is getting at. That's what this formula is.
Oh, okay.
And this is pretty cracked because like let's test it on here. Um, if we test that formula on this guy, um, our A our A in this case is 1, right? Our B is 4, right?
Yeah.
1 second. Does that look wrong? Oh, sorry. Yes, I tripped myself. This is supposed to say minus 2. Um, minus B over 2A. So we have minus 4 over 2, which equals to minus 2. And that gives you this guy, the minus 2 axis of symmetry. Does that make sense?
Yeah.
Now, where this comes from is actually, we can figure that out now, but we'll ignore the A for us. Oh, should we ignore the A? Yeah, no, we'll talk about that now because the completing the square question that I gave was an easy one as well. So sometimes they're a bit trickier, which we'll talk about right now. Um, yes, so let's talk a little bit about where that formula comes from and the hard, if you have an easier or harder example for completing the square. So The hard thing is choosing this number. Now, here was easy because I had already given you four, right? We knew that this thing gives us nicely the equation we want. Um, but the most tricky thing about completing the square is finding this number that you need to be here, this constant number over here. So the way to figure that out, actually, do you know, like if I was giving you x squared plus, let's pick a different number, 3x, or maybe I'll pick 6x plus 1 or something. How would I
Yeah.
know, how would I complete the square with this?
Um, I'm not sure.
That's okay. So the tricky thing is knowing what number to actually add here, right? So that we
Yeah.
can complete the square on this. So to do that, remember our end goal is to factorize this into something that looks like x plus something the whole squared, right?
Yeah.
Now, if we expand this, let's keep this something, it will expand to x squared plus 2 times that something we have, right? X. And then plus that something squared, right?
Yeah.
Now, again, we want to turn this into this. So, sorry, maybe I should have just used a letter, made this easier. So if I call this x plus d, 2dx and d squared. Um, so we need, if we want this guy to equal this guy, we need 6x to equal 2dx, right? And the term we want to add is d squared. That's the term, the magic term we have here. If we hypothetically have this d squared term, then our parabola or our quadratic will factorize exactly into what we want here. Um, so this is a bit of a tricky point to get, but if my 6x or if 6 is equal to 2d, right?
Yeah.
What will d squared equal to?
Um, 9.
And how did you get that?
2D is 3 times 2.
Very nice. Very nice. So you first divide this by 2 to get d, and then you square it to get your d squared, right?
Yeah.
Perfect. Awesome job. And that's exactly the term we want here. If you get 9 here, this guy will factorize perfectly as x plus 3 squared. And you can confirm that if you expand this, it's going to give you exactly this. So this is the trick when deciding this number. You do exactly what you just came up with. You take your, if we call this b, you take b, um, let me get rid of all of this stuff for now. You take this b number and you first divide it by 2. So you do b divided by 2. That's how you got 3, right?
Yeah.
And then you square it. So that's why completing the square, sometimes you see this b over 2 squared.
Yeah.
That's the term you want to plus so that you can complete the square. So the general technique for completing a square is you just do b over 2 squared minus b over 2 squared. So like you've changed nothing. So let me give you another example. Let's get rid of this. And let's imagine I gave you x squared plus 8x minus 4. How would you complete the square for this? What's the magic number first we want?
Um, so do we just plug in that formula for this
So
equation?
this formula tells you the number you want, that constant number you want. So first work that out. What is the number we want?
It's 16.
Good. So we want x squared plus 8x plus 16, right? But
Yeah.
obviously we can't just do that for free. Like as in we can't just change this whole equation. So if you want 16, but currently we have -4, so one way of doing that is sometimes this is probably the best, like the most easiest way, is you just write plus 16 minus 16 and then you keep -4. So we've done nothing to this equation, right? Because we're doing plus and minus 16.
Yeah.
So we haven't changed the equation, but now we can just focus on this part because what does this factorize to now?
4 and 4.
Very good. So x plus 4 squared.
Yeah.
And then we collect these terms at the end. So -16 minus 4 gives -20.
Oh, okay.
And now we're where we want. So this is the general technique. So step 1, find that b over 2 squared term that you need. Step 2, you take your quadratic, your x squared plus bx, and then you plus b over 2 squared and you minus b over 2 squared. Step 3, you factorize this part. This part factorizes to x plus b over 2, the whole squared. And then you just minus whatever junk you have on the outside.
Okay.
Make sense?
Yeah.
Nice. Very nice. Now, to end off, I will just say two quick things. First thing is I said that this is somehow linked to the axis of symmetry thing that you said. The reason is if you assume a equals 1, this formula minus b over 2a, because here we've always been dealing with monics so far, right? If
Yeah.
a equals 1, this formula is just minus b over 2, right?
Yeah.
Now, where have you seen that number before?
Oh, I'm not sure.
That's okay. It's a slightly different. We've been talking about b over 2 squared, right?
Oh, yeah.
But the b over 2 is exactly what ends up being in our factorized form. So notice the axis of symmetry thing we did. You know how we used this formula and got -2?
Yeah.
That 2 is the same as the x value here. Remember this formula, this x minus h, that determines how much our parabola goes left and right. Yeah.
Yeah.
And so the number that ends up here will always be the same as the minus b over 2, because that will be the x value of your axis of symmetry. So it's not super important to know, but just as a connection, the value you end up finding here, which tells you the x value of your the axis of symmetry, is also the same as the one you get from using the formula.
Oh, okay.
Yeah, so you can use completing the square and get your answer and graph it, or this formula also tells you the x value of the axis of symmetry. Now the last thing I will just say, all quadratic formula where you have y equals ax squared plus bx plus c. Oh, sorry, like where you can solve this, right? We're not going to go through it. Maybe we can next time if you want, but if I were to do, so if I factorize out the a, you get x squared plus b over ax plus c over a, right?
Yeah.
Now, if you do completing the square on this, like we have something now that we can do completing the square. We can sort of do the divide by 2 and square this. If you apply completing the square to this, that's where quadratic formula comes from. It's not like a magic formula. You could literally confirm this if you'd like. If you apply completing the square to this uh, quadratic with these general letters B, A, and C, A, you will end up, and then if you solve for it, you will get the formula of y equals minus b plus or minus. That's where it comes from. So that's another use of completing the square. It is used to actually derive. Sorry, I said y here. It's meant to be x. It's where we get the quadratic formula from if we just apply completing the square on this.
Oh, okay.
Yeah. Um, cool. I feel like that was a lot. So quick recap. Um, Parabolas, equation to graph. You can always sub in points, but factorizing is the quicker way. Um, we can factorize monics by looking for two numbers that multiply and add to give this. That gives your answer immediately. If it's non-monic, you got to do this extra step of multiplying it. And that's when you can come up with the numbers. When you can't come up with the numbers, you got to rely on like quadratic formula or completing the square. And that's what we then spoke about here. So completing the square, the key thing, you find this b over 2 squared, then you plus it and you minus it, and then you can turn it into this turning point form.
Yeah.
Any last questions before we end? Perfect.
With the minus b over 2a formula, can't you just use that to find x and then use that to find the y coordinate?
You're saying when we're graphing, if our objective is graphing, your question is, can I not just use this, find the x value, and then also find the y value, and then I have my turning point?
Yeah.
Yes, you're absolutely right. That would work if your objective is just graphing, that works completely fine. Sometimes they will ask you explicitly to find the turning point form as a question. So for that reason, it's still important to know how to do completing the square. But you're right. With this formula, you can do that, and that'll be faster. That's a really good point. Yeah.
Okay.
Does that make sense?
Yeah.
Nice. Any other questions?
No.
Sweet.